let's continue on the topics of material. As I said at the beginning of Tuesday lecture, we need to spend like at least two lectures on material. Although this course is about manufacturing, but without the knowledge on material, we cannot really do a good job in manufacturing. We categorize material to four main categories: metals, polymers or plastics, ceramics, and composites. And we also review the fundamental properties of manufacturing, which we call them, we divide them to physical properties, mechanical properties, and heat treatment properties, basically for a metal, for a material. So today, let's continue with each of these categories. And again, as I said at the beginning of Tuesday lecture, here we're just going to briefly review things. So later you can maybe do research on your own or take other courses, because really to learn about materials and their property is just a degree by itself. So metals. We may ask some question such as why some metals are hard, some are soft. Like, for example, why tungsten is so hard, why lead is soft. And by hardness, if you, let's say, use a sharp tool, you can easily penetrate into lead, but no luck with tungsten. Why some material are brittle and some are ductile. And you know the definition of brittle and ductile. So in simple word, ductile, you can bend them or create a large deformation without breaking them. But brittle material, you can break them without any deformation. So for example, cast iron is a brittle material, while aluminum and copper are soft material, ductile material. Why some material can withstand high temperature? For example, I can think of tantalum, which is a metal, can go up to 3000 degrees without being melted. While, for example, tin, if you go to maybe 220 or 230 degrees, then it's gonna get melted. So the answer to this is three reasons. The first reason is the atomic bonds. In other words, how the electron and protons in atoms in metals are interacting with each other. The second reason, how atoms are sitting next to each other. Is it, for example, a body center cube like this one, which we can show it by BCC, one atom at the center and 8 at the corner of this cube? Is it a face center cube, or it is a hexagonal close pack like this configuration, or maybe any other configuration as well? But more important, it is the grain size and their boundaries. So what is grain size? So let's say if we have a molten metal and we leave it, let's say, at a colder temperature, so crystals start forming. So we say crystal begins to form and solidify. So, and these crystals at different regions of the molten metal start to grow to grains. So grow to grains. For example, this is a schematic of grain for a certain, let's say, metal. Again, just a schematic to give you an idea. So this one, let me make it smaller, put it there. So this one, as you can see, we can have like large grains like this one or tiny grains like that one at different regions. And as you can see, there can be different boundaries between grains. Depends on the grain size, the properties of material can change. As a rule of thumb, we say the larger the grain, the more ductile or more flexible the material is. The smaller the grains, the higher strength and stiffness the material has. So if let me bring another picture. So if I want to show it in a diagram, so maybe this one is a good one. So let's say if we start with grain number 1, which is the largest grain here, and then we go with 2, 3, and so on. And 8 is has the smallest grain size. So we can say as we move in this direction, the smaller the grains, it's going to have higher strength. But the flexibility is the opposite way. So this one is going to be higher ductility. All right. So then the grain size is another factor in the property of a material. Also, since we are going to study the manufacturing processes, there are manufacturing processes that change the shape of grains and their boundaries. For example, let me again bring another image, maybe this one. Like this one, which shows a simple rolling process. And what is rolling? So a piece of metal or a sheet of metal goes between two rollers and the thickness decreases. As this schematic shows, the grain size before the rollers and after the rollers, they are different. The volume is the same, but the boundary of the grain has changed. And this change in the boundary and the grain shape and maybe the entanglement between grains totally change the property of material. So we should keep in mind as we change the grain size and the interaction between grains during the manufacturing process, the properties also may change. So now,
can I ask a quick question?
Go ahead, Daniel.
So when you do a process like rolling and you get sort of the grains that are sort of longer in one direction than the other, does the material become stronger in one direction than the other?
That's a very good question. As a matter of fact, it is. So Daniel is asking, which is a good question, when we do the a process such as rolling, like this one, you see the grains. Let me zoom to that image. So you will see the grain, they change and they becomes longer in one direction and smaller in another direction. So it means the property of this material is going to be different in, like, let's say horizontal or vertical direction. The same process like in forging, the same things may happen, which when we get to forging process and rolling process, you will see, and we have formula to sort of calculate and estimate how the module of elasticity and the strength of the material may change because of these changes. But the short answer to your question is yes, the property is going to be different in X and Y because now the grain entanglement and the way that grain has been put together is changed. But how we can quantify it, we leave it until we get to the module for more, forging and rolling process. All right, so if you recall, we categorize metals to two main categories, ferrous and non-ferrous. The ferrous metals, it was iron and steel. How we make iron, again, I posted a video for you guys, hope you watch it, but simply we mix iron ore, limestone, and coal. We put them all in a furnace, And the function of limestone is to react with impurities. So to react with impurities. So we can get rid of the impurities. And the function of coal, of course, is obvious, to generate heat. So we mix them all in a furnace, we melt them, and then like in a complex system like this, which again, there are videos which I posted on Canvas. Hopefully at the end we get iron. But the material that we get has also other components in it. For example, it has carbon, maybe something around 4%. It has silicon, maybe something around like 1.5%. And other things like magnesium and maybe other impurities as well. So if we can sort of get rid of some of these impurities and maybe add other components, then we will make a better metal, which we call it steel. So how we do that? So the process again is to get rid of or reduce the impurities such as silicon and carbon and magnesium, and also to add other components, which when we discuss different variety of steels, we will see which component we can add. How we do the process, again, in theory and on paper, it's easy. So we put all the metals, the ions, in a furnace, we melt them, and then we add more limestones. And again, the function of limestone is to react with impurities, so we can get rid of the impurities. But the main function of these steel making process or furnace is blowing oxygen to molten metals. What does it do? The oxygen is going to combine with carbon, and we're going to get CO and CO2, and maybe combine with other impurities, and we get them in form of gas, and then we get a more pure metal, which we can call it steel. But speaking of that, there are three types of steels, and the main difference is how much carbon is in the iron or in the steel, and also what other material we added to the basically a steel. As a main category, we can say there are three main categories of a steel: the carbon steel, the stainless steel, and the high-speed steel, which the acronym of the abbreviation of HSS is very common, and probably you've heard it before, which stands for high-speed steel. The carbon steel has three sub-categories. Again, not exact numbers, but as general, we can say low carbon, which means the amount of carbon is less than 0.3%. The medium carbon, which is something between 0.3 and 0.6% carbon. And high carbon, which is bigger than 0.6 carbon. And we don't add any other material to the steel. So it's just low carbon, medium carbon, and high carbon. But the amount of carbon steel is way less than iron, because for iron is 4%, 5% or more, like cast iron. So if like we want to mention how the properties is changing for these, we can say as the amount of carbon is increasing, like from low carbon to high carbon, the hardness is increasing. So hardness increase or goes up. But stiffness is the other way around. So stiffness increase. And Again, as general, we can say the low carbon, they are very common to be used in bolts and nuts, in sheet plates. The medium carbon in gears and crankshaft. Like 2 examples we can say. And high carbon maybe in cheap tools. People use it because we need basically better hardness. What is a stainless steel? Stainless steel, in like simple word, we can say it's a low carbon, like the first one, plus adding 10 to 12% chromium. So this is what we call it stainless steel. What does this, in fact, this chromium do for us? It creates a layer of oxide chromium or chromium oxide, and prevent corrosion. All right, so corrosion too long. So adding 10 to 12% chromium make the steel stainless steel. And this is what we like, stainless steel. Unlike iron, the surface is not going to get rusty or get corrosion, all right? But it needs 10 to 12% chromium. And what is HSS? Again, HSS is low carbon plus 15 to 18% tungsten. And tungsten is a very hard metal. It can withstand very high temperature. And if we add like 15 to 18% tungsten to the low carbon steel, we will make something which we call it HSS. And it has a lot of function in tools and like dies. Later we will see for forging, when we need dies, we will see that we need to calculate how much temperature goes up, which in fact temperature goes up very high, and we need something to withstand those temperature. And this is where the HSS can be useful. All right, so let me also write down that one. This gives us something that can maintain its strength and hardness at elevated temperature. All right, so again, as a general rule, 3 types of steels: carbon steel, stainless steel, and high-speed steel. And now you know the difference. Is there any question before I go to the next part? So I take silent as there is no question, so let's move on. The second category is non-ferrous metals. And there are a variety of non-ferrous metals, such as aluminum, copper, and you name it, titanium, tungsten, tantalum, and so on. Their application depends on their property. For example, aluminum has a lot of application. For example, we can mention beverage can, or something around 70 to 80% of airplane, particularly Airbus and Boeing, body is aluminum, which is a lot. Copper for electrical wire is very useful. For titanium, We can say, because it can withstand high temperature, for example, jet engine, or for human implants. It's a very useful material. Tungsten for tools, tantalum, for example, for rocket engine is again a material that we use it a lot. So in general, they have a better corrosion property or corrosion resistance. Their thermal and electrical conductivity is higher, but again, it varies, depends on the material. Density varies, but in general, lower density. And fabrication is easier, especially with aluminum, copper, and magnesium or nickel. But for tungsten and tantalum, maybe a little bit harder, but depends on the type of methods that we want to manufacture things, which we will get to that point where you learn how we can deal with this hard material when we want to manufacture something and the process that we need to use. And another subcategory of non-ferrous metals is the refractory metals. We use the term refractory because they are very stubborn to change, and that's why they are called refractory alloys or metals. They have a very high melting points and they don't like to change. They are stubborn to change. And there are 4 of them: molybdenum, niobium, tungsten, and tantalum. And again, depends on the application. We may use them for like rocket engine, gas turbine, or nuclear power plant, or chemical power plant, which all of these application requires very high temperature. That's why these metals can be very useful for us in those applications. All right. So before I go to the next category of material, is there any question related to metals?
There's a question in chat about steels. Mark asked, the melting point of tungsten is over 3,000 degrees Celsius, while iron boils at 2,800. How can we allow these metals together?
All right, so over here, right? So that's a good question. So Mark, you said ask? Yeah, Mark. So Mark is asking, the melting point of tungsten is like something around 3,000, but iron is lower. How we mix them? So in fact, that's a good question. The way we do it, we don't melt these two and then we mix them. We make tungsten powder and we mix it with basically with steel, which you will see when we go to casting how we can do this process as well. But the short answer is you make tungsten in form of powder and then you mix it with the iron. Does that answer your question, or you had a more specific question? Silent, I'll take it as yes. All right. So let's go to polymers. Polymers or plastics, they can come in different form, different colors. And if you look around you, a lot of things made out of plastics. And considered to be the bad boy because it has a lot of environmental impact. But because of its property and its low cost, it's very popular. And hopefully in future, human can invent something better. You know, the invention of plastic saved a lot of elephants. If you watch one of those videos for injection molding, so you saw the history of when somebody invented plastic and he saved a lot of elephants because they killed elephants for their ivory until somebody invented plastic to make those for decoration and stuff. But we see plastic makes a lot of environmental impact and it's bad. However, we cannot replace it now with something better. Maybe in future, we'll see. Why it is so popular? Well, because of its property. Besides, as I said, very low cost. Of course, compare with metals. If we compare it with metal, it has lower density, lower strength, lower module of elasticity. its thermal and electrical conductivity is very low, which can be useful if we use them for insulators and so. But this is where it becomes very useful when we compare its specific strength. If you recall, we said the ratio of strength, or SY, yielding strength, to weight. So because it's a lighter material compared with metals, its specific strength is higher, and that's why it is so attractive. Also, it has other good properties. Corrosion, we don't need to be worried about corrosion, unlike metals. The thermal expansion is high, sometimes can be negative, sometimes can be positive. Of course, it can come in different colors, and it can be transparent, which is a good thing. Also, when it comes to manufacturing, you will see it is very easy to make complex shape out of plastic, while with metals, it's not that really easy. We mentioned the electrical property and thermal property. And also, when we make something out of plastic, the surface finish, we can leave it as it is. While with metals, maybe after forging, we need to do extra step, which is machining. While with plastic, in most of the cases, you don't need to do extra things, so which make it cheaper. And it comes in different shape and form, for example, film, sheet, plates, rods, and so on. What is plastic or polymer? What is this structure? So polymer, we can say, like English-wise, it's made out of poly plus mer, which poly means many, and mer means unit. I don't know Greek, but I just look it up. So many units. This is where the word polymer comes from. But why we call it many unit? So let's look at one example. Let's say, for example, if we look at ethylene, let's say ethylene. So what is ethylene? It is a bunch of carbon and hydrogen. So let's say one carbon here, carbon, and then we have hydrogen, hydrogen, and hydrogen, and hydrogen. This is what we call ethylene. So this is one unit, or one mer. Now if we make a chain of these units, so like adding similar one here, and we repeat this, and also here, same things, another unit, or another mer there, then we will get many mer or polymer. All right, so we get a chain of these basically thing, which now we call this one polyethylene. So this chain can link together, or they cannot link together. Let's say if I have one chain, this is the chain, and each of these, let's say, is one of these units. So if I have several of these chains, and if they are independent and no link between them, we call the result a thermoplastic. If there is cross-link between them, so cross-link, let's say this is one chain, another chain, another chain. Now, between these units, let's say there are cross-links. This we call it a thermoset. And if there is a network of these polymers or these chains, like a network, so they join together, one with each other, and so on. You get the idea. Then the result is something we call it elastomer or rubber. And the main difference between them is, as I said on Tuesday, the thermoplastic, you can remelt it and reshape it. But thermoset, when you melt it and it becomes solidified, then there is no way to come back. So you cannot remelt, right? So, but it depends on the application we want. Sometimes we want the first one, and sometimes we want the second one, which when we get to the injection molding, you will see their application as well. But right now, for example, you can think of in a kitchen pot, the lid, the handle for the lid, we don't want it to, when we are cooking something, to get molten. So we better use thermoset. We better use something that it's not become molten again. Elastomer or rubbers, the same. We don't want under heat, they becomes molten and they change their property. Each of these materials, like these polymers, have an important property. Beside the mechanical and physical properties, they have a unique property which is called glass temperature or glass transition temperature. And what is a glass transition temperature? Is a temperature below the melting temperature. And it's a temperature that, in a simple word, the material or the polymer becomes soft and formable. And that's an important property when we want to make things. For example, last year, students, when they made their mask, they need to calculate the TG or the glass transition, because you need to get the temperature of the plate to the right temperature. It has to be just right. If it is hotter or colder, you don't get the product that you want. And let's say if graphically I want to show it. Maybe if this is the x-axis to be the temperature, let's say the y-axis to be module of elasticity. So this one is E, module of elasticity, and x-axis temperature in degree Celsius. So we can say E for polymer is going to decrease slowly, and at a certain temperature, E is going to drop suddenly, and then it's going to become almost zero at some point. So let's say if we denote this point as room temperature, this is temperature of room. This end point to be the like temperature where the plastic becomes molten, Tm, and module of elasticity becomes very close to zero, but not zero. Then the temperature we call Tg is when we have a sudden change. This is where we call Tg, or glass transition or glass temperature. For each metal, for each polymer, we can look it up in tables. For example, for PVC, which is an acronym for this long name, PVC, the melt temperature is 212, but the glass transition is 87. You see, it's way below the melting point. For some polymers, so it's weird, but it is negative. For example, a rubber, you need to get to minus, I believe, 75 or something when you can easily shape it. So it's a negative values. So, but again, when you want to make something out of a polymer, you need to have this number for your calculation and other things that you need to do for making stuff. Is there any question so far?
Can you once again explain what is TG and TM? Sorry, I didn't understand it very clearly.
So TR or T room is the room temperature, the environment temperature that the property is in, the polymer is in, right? And whatever you have now in your room temperature, so nothing is going to change. But as the temperature increase, then there is a point where suddenly the module of elasticity of the plastic drops. You see, there is a sudden drops. And that point, we call it a glass transition. Physically, we say it's a temperature where the plastic becomes very soft and you can bend it, deform it to the shape that you want. It hasn't been melted, but you can basically form it the way that you want. Right? So that's what we call TG. And basically, we don't need to calculate this TG. We look it up because they find this TG by doing experimental tests. This table, keep it as a reference for yourself. It's going to be useful. In future, if you want to make something and you need certain properties, you can decide what to pick. Again, for example, last year when I asked a student, you need to go and buy plastic for making masks. So they, at the beginning, they weren't sure if they should go with ABS, polyester, polyethylene, or what they should pick. Or if you want to make gears out of plastic, then what you need. So first, you need the property that you need. Do you want something to be wear resistance? Do you want something to be chemical resistance? Maybe you are making containers for chemical stuff. Then these are the material that maybe you should go for. So keep this table as a reference. You don't need to memorize it, but that's a good reference to have. Of course, you can always look up things on the internet, but this is something that can be used as a good reference. Let's say you want to make power tool, maybe you go with ABS, or which ABS again stands for this long name, which we use it a lot in tools and stuff. All right, but check that table later with details. So far we check plastics and we check metals. Both are good, they have good properties, but there are certain applications that we need the best of, let's say, best of both worlds, best of these two things together. We want the best of metals. For example, we want something to be, let's say, withstand high temperature, so we go with metals. But at the same time, we want something to be electrical insulator. So we say plastics are very good to be used as electrical insulators. So what if we want, for an application, we want both. We want a good electrical insulators, and we want a good material that withstand temperature, right? So this is where we need something different, and this is where ceramics becomes important. A few examples, like this car spark plug, like this portion. This is where you need something that can work in high temperature. At the same time, you want it to be electrical insulator. No metal can do that for us. So, or let's say tiles, floor tiles. You want something to be good in abrasion, but metal is not a good option because it's going to be very expensive, right? And the thermal expansion, imagine a floor with metals. So when the temperature goes up, what's going to happen? And also it's going to be very expensive. Unless you are very rich, you live in maybe in a palace and you use gold for the floor. Or maybe small ball bearings, the one that I just show in these pictures, the tiny ball bearings for miniature robots or miniature applications, that at the same time you want these tiny ball bearings to withstand high temperature. With steel, you cannot do that because the temperature goes up and they deform, or you cannot make them, in fact, even if you go with the metals with very high temperature. Or let's say your car windshields. So you want something transparent, so you may say I go with plastic, but plastic is not really good in abrasion resistance. So this is where metals and plastics cannot satisfy your need, and we need something different. And this is where we need basically ceramics. So in general, ceramics, they are very brittle material. They can break easily, so you cannot shape them or deform them. And they have very high strength and high module of elasticity, and their hardness and all of these properties can stay the same even at very high temperature. They crack easily. If you remember, another mechanical property was toughness. Toughness was how strong in terms of crack propagation or when we impact them. So they are very low in toughness, and also their density low, which can be a good thing. And also their thermal and electrical conductivity is 0 or very low. So, but what is ceramics? So traditionally we have clay, which we call it traditional ceramics. So it is clay which can be used for pottery, for bricks, for tiles, pipes, like the cheap stuff in construction that people use. Or maybe your mug is made out of clay, which is sort of a ceramic. But the type of ceramics in this course that we will discuss and we will use, it's called industrial ceramics or engineering ceramics. And again, it can have application in jet engine. It can have application in for example, in a rocket engine and so on. And the type that we have, there are, again, variety of ceramics. Again, keep this table as a reference. You don't need to memorize anything, but as a general rule, we can categorize ceramics to oxides. So the oxide ceramics are alumina and zirconia, Al2O3 and ZrO2. And there are carbide ceramics. No, not that one. The carbide ceramic, which tungsten and titanium are the two most important ones. And then we have the nitride, like boron nitride, and silicon, the cermets, glasses, graphite, diamond. They are also important ceramics, which each of them has its own application. For example, diamond may be used for like cutting tools, like a small cutting tools, or glasses. You know, glasses can be used for like a car windshield or other application as well. Alumina and zirconia, you will see later many applications for those. Their hardness and their strength can withstand in even very high temperature. Is there any questions so far, guys?
Just a quick question. So these ceramics are naturally found in the environment, or do we have to also do a process to make them?
No, we have to do a process to make them. That's why we, as I said, we have traditional ceramics, which is like clay, but with industrial ceramics, which they have fire grains. Still, we get the ore and the main material from mining and from nature, but we mix things together to make them. Right? I will post something related to how some of these are made. for your interest, if you are interested, you can check, for example, how glass is made or how alumina or zirconia are made. All right. So you guys are okay to stay for maybe another 10 minutes so we can finish up this part?
Okay.
Okay, all right. So that's good. I'm sorry for keeping you maybe longer, but we better finish it. If you are in a rush and you need to go somewhere, of course, I'm going to post the video on Canvas and you have access to the notes and to the video. So far, let's see what we got. We have metals, we have plastics or polymers, and we have ceramics. Each of them different properties, and they most of our needs can be satisfied. But we, human or sapien, we are greedy. We want more, right? To get more, now we need to mix these things. But why we need more? Well, maybe this graph can tell us why we need more or why we are greedy in terms of materials and their properties. Let's say if x-axis is the specific stiffness. And again, to remind you, specific stiffness is modulo of elasticity per density. And the y-axis to be the specific strength, which is Sy, the yielding stress or strength over density. So ideally, we want a material to be around this corner, right? We want something to be very strong, high strength, and high stiffness. But at the same time, we want something to be light. But unfortunately, like metals, they have high strength and high stiffness, but metals, they are heavy. And we ended up at this corner, the corner that we don't like. With plastic, maybe their specific stiffness and specific strength is higher. We are a little bit happier, but they cannot satisfy many other requirements that we have, such as the temperature. With ceramic, a little bit better, but still not that good, all right? And some of the ceramics, maybe they have very like good strength, but low stiffness. And again, we are not happy. So how we can then make a metal, let's say a material, which move to that corner? Well, maybe we should mix different things together, like the metals, which stay at this corner with plastic. Then maybe we can shift to the upper right corner, which we make a material that has good strength. At the same time, it is lightweight. And just to show you how popular composites are, if we and how new they are. If we look at just example of Airbus, A here stands for Airbus and B for Boeing, we can see from this graph that not long time ago, 30 years ago, there was almost zero, right? 1980, zero composite. But we'll see like in 30 years, almost 50% of Airbus and Boeing is a composite material. So it shows basically the popularity of these materials. And the main reason, again, is the cost of fuel, specifically for Airbus and Boeing, because we want lighter material. That's why we switch from metals to more like composite material. But what is a composite? Again, as I said on Tuesday, composite is something which is made out of fibers and something that contains these fibers, which we call it matrix. So the matrix can be plastic, metal, or ceramic. That's why we categorize the composite to plastic matrix, metal matrix, and ceramic matrix. The fiber, the same, can be plastic, metal, or ceramic, but more popular one are metal and ceramics. But something we need to keep in mind is the property of a composite now. The property or properties of composite depend not only to the property of fiber and matrix, so properties of its fiber and matrix, whatever material we use, it also depends on the configuration. As I'm showing in this picture, so we can configure this fiber and matrix in different way. And each of these way gives us a different property. We can mix them together. For example, as you can see on this laminated, each layer has one of these configuration for fibers in a matrix. Or it can be like this honeycomb shape, and we get a totally different property for the matrix. Another table which you should keep as a reference shows the popular fibers and popular matrix. Start with matrix. The matrix can be like thermosets and thermoplastics for the category of plastic matrix, metals, and ceramics. So, and you can see the popular one for metals, for example, aluminum, lithium, and so on. And for thermoset and thermoplastic, the popular one. In terms of fibers, most likely many of you have heard things with fiberglass. Carbon also is very popular if you are rich and you can buy one of those bicycles, which the fibers made out of a composite carbon fibers, which they are very light, but of course very expensive. Boron and also Kevlar, which another name is for armids, is very popular as well. Which again, you can look up this table if you need in future to check something in terms of composites. But that's an area which there is a lot of development and a lot of change in it. All right. And then the last part of today's lecture is just a quick calculation, how we can calculate the module of elasticity of a composite. Let's do a quick calculation together and we end this module by this one. Let's say I have a simple bar or maybe a simple rod. For simplicity, let's say this is the rod. And so let's say this is a rod that we have, and inside this rod, let's say we have the fiber, a tiny fiber like that. So please accept this picture. This is a schematic. All right, so this is the fiber, and this guy is the matrix. Like a very, very simple scenario with just with one fiber and maybe a matrix in the form of a rod. All right, so we want to find out if we know the module of elasticity of fiber, let's call it EF, and if the module of elasticity of matrix to be EM, we want to know the module of elasticity of basically the matrix, the composite, let's call it E composite. That's the question we want to find out. All right, how we can solve that? Very simple, from the stuff that we learn in MEC 2 or MEC 260. So the way that I can solve it, let's say I assume that this rod is under tension, maybe load F, all right? And we assume that this fiber and this matrix, they bound together, they are not gonna separate. So if that's the case, then we can write down that this total F, a portion of it goes to the fiber and a portion of it goes to the matrix. So let's call it FC, like the force for the composite, right? So they are not going to be equal. Why? Because their area is different. Let's say this is the area for the fiber, we call it AF, and the area for the matrix, let's call it AM. I can see it's 6, but in a minute we will be done. So I can write down the area of cross section for composite is AF plus AM, right? So I need another piece of information so I can solve this problem. And that piece of information is, we know that the formation of the composite is going to be equal to the formation of fiber, and it's going to be equal to the formation of matrix. Because we said these two are bound together, you're not going to separate. So if I apply this FC and these things elongate, then all of them is going to elongate the same amount. So from here, the simple formula, if you forget, FL AE, so FCL, the length is the same for all of them. AC and EC, it is FF, L, AF, EF, and AM, L, it's going to be AM, EM. All right? So based on this information that we have, like this formula 1, 2, 3, and 4, and also let's assume that the ratio of matrix to fiber, and also this can be the volume of the matrix to volume of the fiber. Let's call it X, like a number. You can call it N or X. If we combine all these formula, which you can try later, we will get E composite equal to X EF plus 1 minus X EM. Right? So that's basically the module of elasticity for composite. And also, if you are interested to find out the portion of load that goes to the fiber and to the matrix, to find the percentage of loads in fiber and matrix, we use like equation number 4, right? If you use equation number 4 now, you can easily find out how much of these FC goes to FF and how much goes to the matrix. Very simple. All right, so that's all. I can wait. Sorry for keeping you guys here, but if you have a question, I can wait. All right, see you later, guys. Bye.